heated up a frying pan and thrown water in it,
Sure.
and you know how it dances around?
Yeah.
Well, that's called the Leidenfrost effect, and basically what it is the water's dancing around in there he goes.
Oh my god. Oh my god.
Okay. And then what we can do is take this. And if we take it and grab it and pick it up, notice it floats
What?
slightly higher.
Wow. That's so cool.
And what you're seeing on the camera, that sort of shutter effect, is because this rate of spin of the magnet is some fraction of the frame rate of the camera. And now you can see that the moisture in the air is actually condensing and freezing on the magnet. So it will pin. Okay, I can take the magnet.
Oh, okay.
Okay. So now while we're waiting for this, how about if I give you my little story and you'll be recorded on the...
Okay. But I wanted to point it at you.
Why do you want to point it at me?
I don't know, just so people know who's talking, you know? What's going on here? What are we looking at? There are three components: liquid nitrogen, a magnet, and a high-temperature superconductor, abbreviated YBCO. The object of interest here is the high-temperature superconductor. It is a ceramic material in the family of compounds YBCO, or yttrium, barium, copper oxide, and when it's cooled to below 92 Kelvin, it transitions to a superconducting state. This means that below this temperature, it has zero resistivity and it expels magnetic fields. Before exploring why these things happen, let's first explore the consequences of having zero resistivity. Resistivity is a property of a material that tells you how strongly it resists the flow of an electric current. Once the nitrogen is poured onto the YBCO and it transitions into its superconducting state, its resistivity goes to zero, which means that we must always have zero electric field. This follows from the constitutive equation. Just from Maxwell's equations, we can glean the fact that both the magnetic flux and the magnetic field in a material with zero resistivity must be constant in time. If this were the only distinguishing property of a superconductor, then that would mean that if you brought a superconductor into an external magnetic field, the superconductor would maintain zero magnetic field within it. If a material became superconducting while exposed to a magnetic field, then those field lines would be locked in place, and the superconductor would resist any change in field. The fact that the flux cannot change also necessitates persistent currents, which are just currents that continue invariably without being driven by a voltage. Persistent currents are evidence to us that superconductors truly have zero resistivity, and not just some negligible value. There have been experiments where currents have been sustained in superconductors for years with no decay at all. If superconductors were to just exhibit zero resistivity, then we would not have seen what we saw. The magnet would not have levitated because YBCO was exposed to its magnetic field before it transitioned. It would want to maintain those field lines passing through it. The magnet levitates due to the Meissner effect, a Upon transitioning into its superconducting phase, the YBCO expels all magnetic fields so that the interior has practically no magnetic field lines passing through. The Meissner effect is a property of thermal equilibrium, and it follows from the London equations. Before we look at these, we can consider how the YBCO expels the magnetic field and maintains zero internal magnetic field. This is achieved by screening currents, which are currents flowing on the edge of the sample that produce fields that are equal and opposite to the applied magnetic field. If we consider Maxwell's equations and a solenoid with an internal and external current, then we can see how the magnetic field created by the screening currents cancel those from the magnet. Superconductors completely screen out magnetic fields and are considered perfect diamagnets. Now that we have zero resistivity, we have an infinite conductivity, and our constitutive equation does not work. Now we need a new one. The London equation will do the trick, and it can also validate the Meissner effect. The London equation relates the current in a superconductor to the magnetic vector potential. Ns is a constant associated with the number density of superconducting carriers. E is the fundamental charge, and Me is the mass of an electron. One thing to note is that this version of the London equation is not gauge invariant, which I think is kind of complicated, but I will interpret it as, in this way of doing things, we assume that the divergence of the magnetic potential must always be zero. If we take this to be true, then this equation is valid. Now I'll give a brief description of how this relates to the Meissner effect. All right, let's see if we can show that the London equation can validate the Meissner effect. This is just going to be a few steps and kind of take some shortcuts, but you'll get the picture. So we start out with the London equation. And then we can take the kernel of both sides. Now we know this to be the magnetic field. So we can change that, right? And so then we can also use one of Maxwell's equations to switch this out. So we know that. So then we substitute that in here, and we get so now we're just looking at a differential equation once we clean this up. This is just a differential equation for the magnetic field in the superconductor. We have this new variable, lambda squared, which is pretty important. It's the London penetration depth. We could write it out. And we'll see this relevance once I write up the solution to this equation. Given certain attainable circumstances, the solution to that can look like this. And so this is if we're looking at the magnetic field. If we have a magnetic field in the z direction, and we're looking at the superconductor in just the x dimension here, then we have, say this is the depth from the wall of the superconductor. Yeah, you see this exponential decay. And this is going to be pretty small, so it's going to fall off pretty quickly. So yeah. Cool. This London penetration depth is specific to a material at a given temperature and can be measured for many different materials. The penetration depth of the YBCO we are using is about 150 nanometers. Now is a good time to mention that there are two types of superconductors. There is a type 1 superconductor, which expels all magnetic fields up until the critical field, which is the point where the superconductor transitions to its normal state due to an increase in externally applied magnetic field. At this point, the superconductivity is destroyed, and fields are allowed to penetrate into the material. There is also a type 2 superconductor, which has a lower critical field and an upper critical field. Past the lower critical field, some magnetic field penetrates into the material, but the material still remains superconducting. It is past the upper field that the material is no longer superconducting, and no amount of magnetic field is expelled. These graphs show the relationship between magnetization and the external applied magnetic field for type 1 and type 2 superconductors. How the magnetic field starts to penetrate a type 2 superconductor after it has passed the lower critical field is key to how the magnet can levitate above our YBCO. In 1957, physicist Alex Abrikosov showed that the magnetic field can enter the superconductor in the form of vortices. These vortices consist of a core of normal metal surrounded by a region of circulating supercurrent. The magnetic field can pass through the sample via these vortices. Each vortex carries a fixed unit of magnetic flux, which is given by Planck's constant divided by 2 times the fundamental charge. It's these vortices that pin our magnet in place. Without these, the magnet would just fly off the superconductor upon expulsion of the magnetic fields.
Superconductors, high-TC superconductors were invented back in 1986, and they hit the market for the institutional users like us back in the very late 80s, early 90s. And when we first started doing it, it was very cool, just like you guys just saw, and it's very cool. But then the high school teachers started buying this and doing it in their classes, and students came to Wesleyan and we showed them that, and it was ho-hum. We saw that in high school. However, getting your hands on liquid nitrogen is a pain. So after a few years of not showing it here because nobody was interested, high school teachers stopped doing it. We started doing it again, and it was cool again. So that was kind of a neat sort of segue in a way that how things come and go and what's of interest to students and when they see it.
Deviate very much. But over the short time that takes.
Second. Yep.
Everything okay?
Yeah.
Well, they both act like they're in a coherent fluid state, that they're interacting with each other when you normally wouldn't expect them to be interacting. So that's kind of what defines a fluid. Fluids are dense, and different fluid elements talk to each other. And in the superconducting or superfluid state, both of the elements, both of them share the fact that different pieces of the fluid interact over a longer scale with each other. And that's what kind of makes them act more like a fluid than individual particles. Once you get beyond, once you accept that they're acting in this kind of coherent state where all the particles depend on the presence and state of all the other particles, then it's easy to just think of them as just a fluid, a liquid. so that's the way I think of both superconductors and superfluids. Once you get into this state, they're going to behave more or less in a fluid-like way because of the locked nature of all the particles with respect to all the other particles.